Good day, everybody. Just to complete the divisor method, I'll just mention, you round at a certain point, and there's all sorts of ways to find the mean of a number. So you get the arithmetic mean, usually what we mean average, and that's right here. If you add two numbers, divide by 2, that's the arithmetic mean. Geometric mean, it's the square root of their product. There's these other means, the harmonic mean. There's some other means we don't use too frequently. The root mean square is somewhat useful as well. So to be a mean, if you have, it has to be homogeneous in that you take 10 times each number. The mean will then be 10 times what you had before. It's symmetric, so no matter switch the order, you get the same value. Also, it has to be in between the min and max, inclusive. So it can't be outside the interval made by A and B. So there's some means. Here's a little article putting them in geometric figures. I'll skip the circle one. If you look at a trapezoid, oops, where is it? There it is. And if you represent the size of the number by a length, so B is whatever length, and A is bigger than B. But if you represent it by a length and make a parallelogram, then the means in the parallelogram, let's see if you go, the harmonic mean passes through the intersection, and the geometric mean makes it so that you'd have similar trapezoids, right? So if you have these two diagonals for the trapezoid, the harmonic mean is going to be at that intersection. The geometric mean makes it so that the ratio is the same as, so that they're similar. And the arithmetic mean bisects. Here's some of the others. The Heronian mean, it's 1/3. That's not too interesting. Centroidal mean passes through the center of mass of the trapezoid. So that's kind of interesting. Root mean square actually bisects the area of the trapezoid. Contraharmonic mean is as far to one side. They have to the right, but I think they were thinking the smaller number would be on the left. So if the smaller number is on the left, the contraharmonic mean's on the right. It's as far as on one side of the arithmetic mean as the harmonic mean is to the left, so it's kind of symmetric that way. If I look at some of the means here, well, let's see, there's one more mean I added, and that's the arithmetic geometric mean, Gauss's arithmetic geometric mean, and that's if you find the arithmetic mean of two numbers and also then find their geometric mean, you get two new means. But then you just repeat the process. So with those two numbers, find the arithmetic mean of those two and the geometric mean of those two, and just keep repeating the process, and you converge pretty quickly. There's the example on Wikipedia. If you start with 6 and 24, well, the arithmetic mean would be 30/2 or 15. There it is. So step 1, we're at 15. The geometric mean, if you multiply 6 times 24, you get 144. The square root of that will be 12. And then just keep going. So the arithmetic mean of these two numbers, 13.5. The product square rooted, it's this number. And if you keep going, it converges pretty rapidly. So here's a table of all the means we just saw, and you can prove the harmonic mean, you kind of saw in that picture, is always less than the geometric mean, which is less than the Heronian mean, which is less than the arithmetic mean, which is less than the centroidal mean, which is less than the root mean square, which is less than the contraharmonic mean. And of course the max and min are saying which these. I put the max right here though. And then Gauss, I didn't look for it, but based on the computing it looks like it's in between the geometric, well, I know it has to be in between the geometric and the arithmetic mean, but looks like it's smaller than the Huronian mean as well, based on my work here. And as stated, if we look at, say, 10 and 20, that's exactly 10 times the result of looking at 1 and 2. Right, so 1 and 2, so it's homogeneous in that way, as all means should be. So this is harmonic mean. That has a lot of nice optimization properties. It's also called Dean's method. If I look at that, so I'm going to round in that way. Here's the harmonic mean of adjacent integers. So 20 and 21, their harmonic mean is that value. But another way to get that mean is if you do the reciprocal of the two numbers. So 1 over 20 plus 1 over 21, average them, and then take the reciprocal of that. And it's a little easier with 1 and 2. So take 1 over 1 plus 1 over 2, and you get 1 plus 1/2 is 3/2. Average them, and I get 3/4. And if I take the reciprocal of that, I'll get 4/3. There we go. Anyway, so rounding in that way, well, the numbers are smaller where we round. So it looks like I got too many, so I need a bigger divisor here. Let's do 767. So with that, there we go. So if I compare, this is the 2020 census. Dean's method is different than Huntington Hill and Webster and Hamilton and so on. So there's all sorts of ways to round. If I look at this example here with 5 states and these populations, it totals 21,000, and I want to give out 21 seats. Well, if I want to do it through Webster's method, oops, I got that down here, with this divisor, then rounding will give me the 21. So it'll be 6, 6, 4, 3, 2, give me the 21. With the Huntington Hill method, I need this divisor, 645, divide each population by that, and then rounding with the geometric mean, it's a little bit different. So compare, so 6, so B did not round up in that case, instead C rounded up. And we're not looking at the geometric mean, but you can, well, actually we have them right here. Well, square root of 6, here it is. So, so C rounded up, 4.477, and you see 4.472 is where it would round up. And this one rounded down, 5.474, 5.477. So it was really close, but B rounded down with this divisor, C rounded up, and that gave me my 21. With the harmonic mean, here they are, here's the roundings. So that's 6, 5, 4, 4. So now D got the seat instead, so that's a whole different result. Again, here's where we would round with the harmonic mean. This is the lower quota there. So find the harmonic mean from where to round. And you can see that D is above 3.429, 3.430. So it rounded up, and these others round down. With Jefferson's method, that's just where you round down always. A got the seat instead. Adams' method is you always round up. Of course, you have to change the divisor, so you use this divisor, then E got the seat. So that's actually 5 different divisor methods, and they were all considered by Webster, and at the end he went with what we call Webster's method, just regular rounding. But 5 different methods, and they give 5 different results for this population and 21 seats. So I didn't change the population or the seats, but just with the method of apportionment, I got 5 different results. Kind of surprisingly, Hamilton actually agreed with Adams on this one. Here I do it with the arithmetic geometric mean. Got the table right there and where the rounding is. This is when I was trying to approximate what the 2020 population was. So this actually isn't correct, but while experimenting, a neat little result showed up. So it's in between the means. If we look at these means, right, so Gauss has to be in between the geometric and arithmetic mean. And so it's often the same. It's actually a little closer to the geometrics. It's often the same as Huntington Hill, but it came up different in my experiment. So in my 2020 estimate population, and also something interesting happened where Minnesota, because most of the time things get monotonic, where it's kind of beneficial for larger states as where you round is higher and higher, because then you have to divide by a smaller number. And it's beneficial to smaller states if where you round is lower, because generally you get too much, so you have to divide by a bigger number, and that hurts the bigger states more. So smaller states usually benefit when you round in this area, and bigger states benefit, say, around here. And it's usually monotonic, so once you lose, you're not going to come back. But I guess it doesn't have to be. Like Minnesota, it dropped down to 7, and then as I changed the divisor for the rounding higher and higher, it went up to 8 and then back down again. So that's an example of not being monotonic. But just a quick look at what would happen year by year. So if I look at, this is the true 2020. So this is the 2020 apportionment based on all the different rules. I separated Hamilton, so the divisors, as where you round gets bigger and bigger. So Adams, you just always round up. The min, you round over the min. Dean's method, the harmonic mean. Huntington Hill, you round with the geometric mean, harmonic mean. The Gauss arithmetic geometric mean and the Huronian mean turned out to be the same. There's Webster. The root mean square and the centroidal mean ended up being the same, contraharmonic mean, and Jefferson. So for whatever it's worth, again, we'll look at optimization results shortly, or in another video, I should say. One other thing also, again, this is another example of where, again, smaller states benefit over these columns, I would say, larger states on these columns. But again, it wasn't monotonic where, so Minnesota got 8 seats, and then it changed to 7, but then it went back up to 8. It stayed at 8 and then went back down to 7. So a little unusual, I would say, but all right. So I think that's that. As mentioned before, it's easy to see Adams and Jefferson have quota violations, but all the divisor methods you can force a quota violation of at least an upper or lower, one or the other, and sometimes not with the same thing, but Webster and Huntington Hill, they can have lower quota violations, or they can have upper quota violations. As shown in this last example, both Webster and Huntington Hill have upper quarter violations, and in this example, they have lower quarter violations. Looking at Jefferson and Adams methods, Jefferson can only have an upper quarter violation, as it did with California and Texas, the large states. And Adams can only have a lower quarter violation, as it did with the large states, California and Texas. They have lower quarter violations. But generally speaking, you won't get quota violations with these others unless it's somewhat of a contrived example. All right, so signing off. Have a good day.